Swayam Prabha. Digital India. Educated India.
Morning, folks. So I'm not going to do anything very heavy duty today, right? So it's more like setting the stage for trying to dispel some of the hype and the myth about AI and all that. There might be a few things that you will pick up along the way that are quasi technical, but I don't intend this to be a fire hose class on AI, right? And feel free to stop and ask questions and things like that. So I do have two sets of slides. This is the first thing is on general introduction to AI, and then there's a second one just telling you what is ChatGPT and what's all this hoopla about ChatGPT and all that. We'll see if we get to that because we have only 2 hours, right? Okay. So I'm going to talk about generally what is AI. Right, these are the two different views of AI, right? So it's either Schwarzenegger coming to get you. Right? So how many of you have seen Terminator? Man, that must count as something. Huh? It's a 1983 movie. Did you know that it's that old? No, thanks, but yeah, no. Anyway, so the old one. I'm talking about the original Terminator. That's the only one worth seeing. None of the sequels. Okay, somebody agrees with me there. Yeah. Anyway, so either you think it's going to come and destroy the world, or you think it's the second coming, it's coming to solve all your problems, make the world into a paradise or anything, but it's not really anything, none of those, right? What it is basically a piece of code, right? It's software, and so why are we all so excited about AI now? So I'm pretty sure most of you know this stuff, but some of this you might not know, right? AI is in everything, it's also everywhere. So I kind of jokingly say, observing how some of my son and some of his friends used to behave, that kids nowadays talk more to AI than they do to other human beings. Right? So you're so happy talking to your phone and chatting away with those and stuff like that. Right? So anything and everything that you use has some amount of AI in it nowadays. Right? So we really need to understand what it is, what is it doing, and where it is taking us, right? So some of these you know already, right? There's this. Is Facebook even a thing with kids anymore? I mean, first of all, I shouldn't call you guys kids. You're all young adults. No? How many of you are on Facebook? It's okay. It's okay. It's not a crime. I'm on Facebook. How many of you are on Facebook? Really? Wow. Okay, what other social media are you on? Instagram. Oh my God. Okay, good. Yeah. And now I know why my son doesn't want me to have an Instagram account. Anyway, the point is, so all of these are fine, but there are also other things like people using AI systems to decide bail cases, bail applications in courts, and then they are using it to decide who they lend money to, right? And now they have started doing credit rating. So unfortunately, I can't point to this monitor. Okay, this thing doesn't come, so I have to point there. So all of you look that side whenever I'm pointing something. Okay, right? But even more interestingly, so how many of you knew of all these things that the AI has been doing? So I can't point there, I have to go here. So that's protein folding. So have you had a talk on protein folding by any chance? You have, right? So that's a very hard problem, as you know, right? Did somebody talk to you about AlphaFold? Who? No, not that. No. It's an AI program. It's an AI program that has 97% accuracy on all the known protein structures. It can predict protein structures with 97% accuracy. It gets only 3% of the known protein structures wrong, right? It's gone to an extent where some people have declared protein folding as a solved problem. So it's basically AI has helped us solve this protein folding. That's in biology. And the next thing up here, right? So there is this something called the knot conjecture in math, right? So which people have been trying to prove or disprove for decades, and then there's an AI system that went ahead and proved the knot conjecture, right? And then that's nuclear fusion, right? And then strange electrons. I have no idea what strange electrons are. I'm sure they are not normal, right? But AI helps you study those as well. The point here is that AI is not only helping you do better Insta posts, right? But I should probably change that figure, right? Remove Facebook and put Instagram on my slides. Anyway, but it's also helping you solve science, right? Do better science. In fact, it's coming to a point where people, at least in biology, are saying that you can't do cutting edge biology anymore unless you are taking help of AI tools, right? It's come to the point that, right? And this is something for healthcare. Okay. I'm just putting these headlines there. So it's basically significant advances in AI in helping solve healthcare, right? So everybody is thinking that the next huge change in whether it be public health, whether it be diagnosis, whether it be drug discovery, right? So all of these things, right, is going to come from AI systems, right? And you can see, I mean, I didn't change the slides, so you can see where I gave this talk before, and a version of the talk, not all of this. So some slides you will see Vellore, CMC Vellore on it, because I was giving this talk to a bunch of doctors at some point. So I had to put in a slide with all healthcare things, right? But the thing with AI is it's not new. Right, so that's Alan Turing, right? And so he said back in 1950 that he wanted to think about the question, can machines think? Right? And he came up with an answer. Right? So people know what the answer is. What did he call his answer? Huh? Well, he was not that much of a megalomaniac to name that test after himself. He called it something else. People later called it the Turing test, right? So anyone has seen the movie based on Turing's life? What was it called? That's the name Turing gave to his test. So he called it the imitation game, right? That's where they took the name of the movie from. He called it the imitation game. The basic idea is that if an AI can imitate a human being, then it is intelligent. And the way he said this is, you basically have an AI and a human interacting with another human blindly, right? So this the second human shouldn't be able to tell apart which is the AI and who is the human, right? If that happens, then he says that AI is truly intelligent, right? It is more like a thought experiment, right? Nowadays, a lot of people who don't know anything about AI and who are giving their opinion on AI seems to think like Turing test is like JEE. It's like an exam that you write and pass. Everybody says, AI has passed the Turing test, right? And no, I mean, it's just a thought experiment, right? It's not, there's nothing like a concrete test that the AI can write and do, but that's where it, the whole thing kicked off, right? Then the word artificial intelligence itself, right, was coined back in 1956, right? Oops. Right, so there was this a small conference, about 10 people. I think there were 12 invited, only 10 showed up at Dartmouth, right? And then they basically discussed about what does AI, what is intelligence, what does artificial intelligence would look like, and so on and so forth. And then they coined the word artificial intelligence for the first time, right? And the goal was to build a computer program, right, that can simulate all aspects of human intelligence. Their idea was to be able to understand human intelligence in a very systematic manner, so that you can write a program that will simulate it, right? So the idea was not to create Arnold Schwarzenegger, right? So they just wanted to say this computer program that's going to simulate this, right? And these were the people who showed up at that. They're amazing set of folks. So all of these guys went on to win what's called the Turing Award, right? So how many of you heard of the Turing Award? Right, the Turing Award is like the Nobel Prize for computer science, right? So 4 of these went on to win Turing Award. Actually, one of them went on to have an award named after himself, so that's even better than winning the award, I guess. So then one person also won a actual Nobel Prize. Okay, so Herb Simon actually won a Nobel Prize in economics for some of his contributions, and he also won a Turing Award for the only person to actually win a Nobel and a Turing. Right, and apart from these guys, and there were oops, I should go back. Turing himself and von Neumann, right? I mean, Neumann is one of those real modern day geniuses, right? So he has done a lot for AI, he has done a lot for computing, right? And so he came up with this whole notion of stored programs computing. It just looks so silly to us nowadays, right? But somebody had to actually invent the fact that programs can be stored in memory, right? And can also be modified, right? So that apparently was a very revolutionary concept back then, and von Neumann came with that. And what else did he do? He came up with this whole mathematical discipline called game theory. He's considered the father of game theory, and also he revolutionized economics because of the applications of game theory in economics. This is one guy who has revolutionized computing at one side, AI, and then economics and everything, right? An amazing guy. So he has done a lot. All of these people have done wonderful stuff, right? So what is Turing's claim to fame? Starting in Enigma code and invention of the computer. No, he didn't invent the computer.
He theorized the Turing machine.
Yeah.
Which is basically, it's built such a way that you have an infinitely long tape, and you have like a reader.
Right. What was it?
It was a universal machine. It could compute
So
anything.
basically, he came up with a way of systematizing computing, right? I mean, so people had various ways when they were writing arbitrary stuff, right? So he came up with a way of basically thinking about complexity of programs, right? Thinking about computation itself, right? Like in a very, very systematic manner. He gave this whole framework. He built this whole theory of computing. So that is his biggest contribution. Apart from, of course, people celebrated him during his lifetime for the Enigma machine, but then the Turing test and all that picked up speed later, right? Yeah, I don't want to say what else they did to him when he was alive, but that's okay. If you've seen the movie, you know what. Right? So basically, this is the take home, right? So AI, the goal of AI is to replicate human behavior, right? Not so there are two definitions that people go with, right? AI. There is a hard AI and something called soft AI. So hard AI is not only do you replicate human behavior, but you try to do it the way humans do it, right? And soft AI is, hey, no, you solve problems which humans are good at, which computers are traditionally bad at, but then you come up with ways of solving it. Doesn't necessarily mean that you solve it the way the computer does, or solve it the way the human does, right? So there is this very interesting quote. You know that back in the 90s, there were these chess playing computers that were creating a lot of buzz around the world, right? So there were this thing called Deep Blue that beat every human, and right now we are at a point where humans cannot easily beat chess playing programs, right? They are so much powerful than even the best human player out there. But when Deep Blue came, right, people were just saying that, oh, Deep Blue really doesn't know how to play chess, right? It just is just a program that is doing a bunch of things. So there was this person who said, hey, saying that Deep Blue doesn't think about chess is like saying that an aeroplane doesn't fly because it doesn't flap its wings, right? So that's basically Deep Blue does not necessarily solve chess like the way humans would solve it, right? But it's nevertheless thinking about the problem and solving it in its own way, right? Just like airplanes fly, right? But just they don't flap their wings, right? So AI is not new. So AI hype is also not new. So can you read this? The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Any guesses when this came? 60s. 60s. You said 80s first and then reversed to 60s. Somebody said 80s, but anyway, 60s. Close. Right? It's an article from 1958. Remember, when was the word AI coined? 56. Already by 58, people are talking about this, right? So, whenever you hear hype about any technology in the press or all that, take it with a pinch of salt. Right? So, real AI success is also not new, right? I mean, game playing is not something it does in the 80s, not something that it did in the 90s, and not something that it's doing now, right? So, this person, the picture is Arthur Samuels. So, he was somebody who was working for IBM, right? And so, he did a live demonstration on TV, on live TV. He went on TV and played a game of checkers with a computer that had actually learned to play checkers. It was not programmed to play checkers like the chess, like the Deep Blue and things like that, right? It actually learned to play checkers through trial and error, and it was very amazing. One of the very first large scale learning programs that were demonstrated. But unfortunately, they didn't pitch it as a learning program. Samuels just came up with this whole idea and then coded it up and made it learn. They pitched it as a demonstration of the IBM 701 and how powerful it was, not the fact that he has actually invented a new kind of AI, which is what he had done, right? People didn't recognize it for another 30 years after, that he had done something really revolutionary at that point, right? Of course, I'm pretty sure most of you in the room haven't seen these advertisements, but when I was your age, these things were coming out, like fuzzy logic in washing machines, fuzzy logic in refrigerators and all that. These are like AI enabled devices that were being sold in the market in the 80s, right? So, it's not like it's something new, but those were mostly marketing. So, what is really this whole idea of intelligence, right? So, we are trying to artificially simulate intelligence and all that. So, what is this whole idea of intelligence? We can try and look at what the dictionary says. There are all various definitions I picked up from different dictionary entries, right? Capacity for learning, reasoning, understanding, and similar forms of mental activity. Mostly vacuous, right? I mean, as people who want to do math or who want to do computing based on these definitions are not really good. Let's try some examples. Playing chess, does it need intelligence? Or let me phrase it another way. If somebody is very good at playing chess, would you say that that guy is intelligent? Or would you say, oh, he's not intelligent, he's just another Vishwanathan Anand? No, right? You're going to say he's very intelligent. I mean, Vishwanathan Anand is obviously super duper brilliant. Okay, I'm just using that as an example. But we have computers that can play chess, right? So, this is something Kasparov said back then. In a few years, even a single victory in a long series of games would be the triumph of human genius. Right? This is what Kasparov said back then. And so Kasparov was very upset when he lost to Deep Blue. Right? And later on, 2020, recently, right? So there was this talk in which Kasparov said he was upset when he lost to Deep Blue, not because a computer had beat him, right? But he was upset just because he had lost in match play. It was the first time he had ever lost an official chess match. Before that, whomsoever he played, he has won. That's what he claimed. He said, I was upset just because I lost, not because I lost to a computer. And he is now a proponent of a new kind of chess, where human computer teams play against each other. So I forget the name. He has a very specific name for that kind of chess tournaments. But he is now he popularizes that, and he says that we should not spurn computers. We should actually use that in a way so that we get better strategies and better gameplay and stuff like that. But it's amazing. So how about proving theorems? Of course, this one takes some effort to prove, but you agree it needs intelligence, right? This is back in the 90s itself, right? So we had a program that could prove that was not known, right? Not only did it prove, right? But New York Times article says that this would have been called creative if a human had come up with it. Because it's an AI that has come up with it, we hesitate to call it a creative proof. How about that? So folks recognize him? Not really. No, this was long ago. He was the ultimate quiz master of India, Siddharth Basu, and they got him on Kaun Banega Crorepati once just for fun, as a temporary quiz master, I guess. But quizzing takes intelligence, right? People know where I am going with this. So that's IBM's Watson engine that was trying to play the game of Jeopardy. Right? Jeopardy is one of the longest running quiz shows, right? And so it beat all the human champions. So Ken Jennings happens to be a guy who was declared the champion of champions. Huh? Ken Jennings, that's his name up there on the slide, right? Okay. So Ken Jennings is the guy who's been declared champion of champion, not once, I think he's been declared twice. Right? So it's supposed to be really, really good, and then you can see the score difference between him and the Watson engine, right? So, and he actually has written there, "I for one welcome our new computer overlords." Right. How about things like vision? Does that take intelligence? Look at these. I mean, can you tell me which of these are boys? Huh? Is it? No, they are real pictures. Real pictures of babies, I know. And Winnie the Pooh, of course. Yeah. Winnie the Pooh is male. Third one. And then that's the only one, is it? What about the first two? Huh? Second one is a? Okay. Good. Yeah. You're right. So the first one is a boy, the second one is a girl, and the third one is very interesting. It's a boy. Okay? But you know in the cartoons that Winnie the Pooh is voiced by a lady? In the book Winnie the Pooh is a boy. Okay, of course from the picture you can't say that obviously, but it is voiced by a lady. You know, Winnie the Pooh has like this slightly gravelly voice thing, right? So you can't tell, but it's voiced by a lady. Anyway, but then computers can do better than humans in vision. But it turns out that a lot of people don't think. If somebody proves theorem or somebody does well in a quiz, you're going to say, yeah, what an intelligent guy, right? Somebody looks at you and say, hey, you are a boy. You're not going to call that person intelligent, right? Okay, he's functional. It's at best what you can say, right? But still, it turns out that those were solved, whatever I was showing you earlier, were solved in the 80s and 90s, and beating vision, right, better than humans, came only in 2015. Turns out that vision is a much harder problem for computers than it is for humans, because our mind is kind of wired, right, to do all these tasks that are required for survival. Things like recognizing animals or recognizing friends versus foe, being able to hear cries of help, right, and being able to vocalize things so that others can understand you, so that you can cooperate and survive, right. So things that were essential for, I'll get to your question. Things that are essential for survival, our mind is wired to learn those, right. So, well, what would have happened if our mind is not wired to learn those? You would have died, right? There probably human race where it was not wired to do that, and some versions of those, and they probably died, right? So it's kind of the fact that we are here tells us our mind is wired for survival, and we have the survival skills, right? Therefore, we are very good at solving these problems, and the way we think of computing, right? The way we have looked at how computers have developed, thanks to Turing and von Neumann and things like that, their computing was organized in a very different way, and so they were useful in solving these kinds of sequential reasoning problems, which were like quizzing and proving theorems and playing games, as opposed to things like vision, right? So it took a while for us to come up with technology where you could do very well in vision. Yeah, go on.
So clearly, AI has the less error rate when it comes to vision, right? Recognizing things. Then why do we still get in captures, point out the motorbikes in the pictures to distinguish?
That's because there are companies that make money out of captures. I have seen really stupid capture, right? One of my banks basically says, please enter the text in the picture above. It's like this. I mean, the actual picture is like this. I have no idea why we have these as captchas. Okay, I think that we are basically testing whether you have eyes, whether you can see it. I mean, because if it's a a very cheap bot that somebody writes, right, it probably doesn't have eyes to see this. I don't know why. So there must be some reasoning behind this and why people sell these captchas. But yeah, computer is very good. So I mean, there are so many papers that out there that where people have developed AI that cracked all these captchas. In fact, now I'm pretty sure the AI systems can crack the captchas with lot fewer error rate than I can, right? Because some of these things, there will be this tiny 3-pixel motorcycle somewhere in the distance, and it will say you didn't catch that motorcycle. I will probably miss it when I'm looking at it and ticking all the boxes with the motorcycle, but the AI probably will catch it. Anyway, so going on, I'll come back to this later. So I'm not going to talk about all of these vague definitions. Let's take a little bit more concrete tasks, right? So I think of intelligence as being broken into 4 things, depending on what we generally call intelligence and what people work on in the area of artificial intelligence, right? So the first thing is what we call perception. So the perception is just taking in information from the outside world, right? So you're either seeing or you're listening to things, touching things, feeling things. So all of these are perception, right? You're taking in information from the outside world, right? The second part is what we call cognition, right? Trying to make sense out of this whatever you have perceived so far, right? So how do you understand text? Can you describe as image to me? I mean, I can take in the picture, right? I can say, okay, there is some set of pixels there that is moving together. There is another set of pixels here that's moving together. So I can think of these as a thing. But if I describe the scene to you, right? So I'll have to do it. I have to understand what is there. Right? I have to say there is like the room with some 50 people sitting in and so on and so forth. Right? So there are a bunch of things that I need to do to understand what I am taking in. So that's the second part, right? And turns out that perception and cognition are the most challenging of the AI tasks that people have been working on over the years, right? And in fact, the first 50 odd years of AI research, right? People were so much better at reasoning and decision making, right? And at learning and adaptation, arguably, but certainly in reasoning and decision making, people are so much better than in perception and cognition. It's only since the 2010-12 time frame, right? Only the last 15 years or so, we have gotten so much better at the interacting with the world part, the vision and understanding scenes and so on and so forth. And that is why you are feeling the impact of AI more and more in our modern world, right? So almost everything that, if you have a phone with you, or if you have a smartphone with you, you probably have like 20-30 AI things running on the phone right now, right? Or you are accessing those services through the phone, right? The reason it has had so much impact on life is because we managed to crack what would normally for humans be mundane things, right? Getting the input in, the perception and some amount of the cognition part, right? And then you go into reasoning and decision making. So where there's a lot of logic, what we call planning. I'll talk a little bit about that in a bit, and then learning and adaptation, right? So learn from from examples, looking at other people and adapting your solutions and so on and so forth, right? So the takeaway here is AI is not a single technology, right? It's nothing like, oh, this is AI, right? So but all of these are various components of AI, and you're going to have various technologies for looking at each and every one of those components. So if you take perception, right? So you have computer vision, right? Things like identify objects in the image, right? Or speech processing. So identify the speakers, identify the words that have been uttered, right? And recognize the music and so on and so forth, right? And natural language processing is about actually understanding the language, right? Actually taking in the language, identify phrases, syntax, entities in the text and so on, right? So obviously AI is very good at doing some of these, right? That is image that I already showed you. And here is our speech recognition, right? So that is the speech recognition accuracy, and again it turns out that the human accuracy level was around 95%, just like in the image setting, and around 2015 the systems were able to beat human accuracy. So some of these superhuman performance results you have to take it with a small pinch of salt, right? Because these testings were probably done in very ideal conditions. Right? They were not probably done on going on a very loud auto rickshaw with two buses going next to each other, and the auto guy says something and you recognize it, right? So maybe not under that conditions, right? But when I'm talking to you on the phone, it probably can do much better than humans, right? And I always say that 5% error that you see there is basically the husbands not listening to their wives. Yeah. So, but that's not true. So all of us listen to our wives very diligently. Yeah.
Sir, a lot of these speech programs also have like a problem with accents. Will that be reflected in these results? Like different accents, for example, Google Assistant cannot like understand accents properly.
Yeah, it used to be a problem. Now things are getting so much better, especially if you're speaking with an Indian accent or a Tamil accent or something, whether it's the Google phone or Alexa, anything, right? Google Home, all of these guys are doing better, right? But this particular graph, right, doesn't take into account accents. This is all trained on proper American pronunciation. So really great success, right? Now we have so many products that are out there, getting superhuman performance. But then there are other things, right? When you get into cognition now, right, there are things like scene understanding, like describe a face, right, or describe the picture, describe the scene that you are saying, right? So you're not quite there yet, right? I can basically identify what are the individual objects on the scene, right, but I can't put together a coherent description of the scene, right? That's still a problem, right? Likewise, speech understanding, right? So I'm talking, right? I mean, there are words, but then there are also pauses, right? There are tonal variations, right? And a bunch of different things that are happening, and we are very good at seeing that, right? So we are even good at correlating how people blink versus what they say and all of that, right? So but AI still hasn't come there, right? We still have some way to go. And likewise, things like usage of idioms and sarcasm, and having tried to have a free-ranging conversation. That's now the boundary is being pushed on that, because ChatGPT can do all kinds of free-ranging conversations, right, including going completely off the range. But still we are getting there, right? It's still work in progress. A lot of work has been happening. Yeah. The mics on the other tables don't work, is it? Anyway, go on.
Sir, I think scene understanding is getting very close to being solved. You have models like Deep Blue and CLIP, which are very, very good at understanding scenes. If you give it like an input image, it's very good at describing that input image to you.
It's getting close, that's what I said, yeah.
The reverse process working very well with models like Stable Diffusion and DALL-E, getting pretty good.
Have you seen DALL-E's or Stable Diffusion? I forget one of those. Render hands.
Actually, Midjourney has solved hands.
Midjourney has solved hands a little bit, yeah. But then that's, like I said, it's work in progress. It's not, I wouldn't declare it as solved yet, right? I'll tell you why. If we get to my second talk, I'll tell you why. So what about reasoning? Right, so we talked about the first two parts, right? We talked about perception, we talked about cognition. What about reasoning, right? So let's take an example, right? How to play chess. So I'm not going to get into all the work that has been done in reasoning, right? Only very simple thing. So how do you play chess, right? The typical AI approach to playing chess is to essentially systematically, don't look at the picture very closely. They're all the same chessboard, cut and pasted, right? But then the idea is that you'll be looking at all possible outcomes when you could make moves, and then you're going to kind of roll it out, right? So okay, let's say if I make a move, what will be the right response that my opponent will make, and then you kind of start rolling it out, right? And then you get pictures like that, right? So every outcome, so you can see this here, right? So from here there are so many possible different outcomes, and then you pick one outcome and then you want to explore that, and then there are so many more possible outcomes and so on and so forth. Now when you start doing this search to longer horizon, right, I'll have to start having some mechanism, right, by which I can prune these, right. So this is the boundary that I have got to, there's so much that I have, right, and then I'm going to say, okay, some of these options I'm not going to take, there are other options I'm going to explore, and then you come up with various kinds of what are called heuristics, right, to say that okay, these are the positions that you have to explore from, these are the ones you can ignore because there is no good way of winning from there and things like that. So, these kind of very large what are called search trees, right, are formed, and then they have various heuristics and other things for searching through these outcomes, right. And so, this is a picture from one of the old news stories. It calls it the cunning deep blue, but the point is this is how deep blue actually played, right. This is how humans play chess, kind of, but not quite, right. Humans actually use a whole bunch of other shortcuts, right, and then a whole bunch of former games that they have played, they have some things in their head about it and they know how they go from there and stuff like that. But the truth is we do not really know how humans play chess, right. There are heuristics in our head, but we do not know how we compute those heuristics. How does, so that is why some people are so good at chess and others are not, right. If you know exactly how humans play chess, we could just basically teach everyone how to play chess, right. So, some people get very good at it, some people still struggle, right. So, obviously this is not how humans play. Look at this, the Deep Blue versus Kasparov, right. So, Deep Blue apparently took something like 15,000 watts of power to play a game, while humans take about 20 watts for operating for over the same period. Of course, the 20 watts is some kind of obviously approximate computation as to how many watts it takes. And then, so this we already looked at the Watson engine, right, and it took 20,000 watts of power. And likewise, this is AlphaGo, which I will talk about in a bit. AlphaGo took 30,000 watts of power. Right? Look at that, 1920 CPUs and 280 GPUs. Now they have AlphaGo playing on 4 TPUs, right. So, the amount of power consumption has come down significantly, but still way more than what a human consumes, right. So, there are a lot of distance to go into getting the AI systems as power efficient as humans, but there is always a trade off, right. So, how about theorems? So, the way the EQP algorithm and others did theorem proving is basically this: you start with some known facts, right, then repeatedly apply various rules of inference, right, and as long as you can come up with a valid chain of these rules of inference, then you get to valid conclusions, right. So, that is basically what they did. It is like starting with the initial board position and then applying the rules of the game. So, you could simply use a similar kind of search tree that we saw earlier, right. With chess, you could use something like a search tree to even prove theorems, right. This is how they went about doing it. So, instead of moves in the board, you have rules of inference that you can use, right. So, these are some of the rules that they were using in the proof. So, the reasoning and decision making space, there is a lot of work that has been done, right. So, you have various theories of logic, right. So, you have decision theory, game theory, planning, right. So, there is a very specific AI sub area called planning, right. So, we know what plans are roughly in our head, but there is a very formally defined notion of what is called planning that actually lets you search through those trees in a very efficient way, even though the trees can be exponentially large, right, but planning allows you to search through those in a very efficient way, right. So, what about learning? So, how do we do breaks? Do I just keep going? If somebody keels over, then we take a break? Huh? Great. Oh, only if I want to give you a break, is it? Then I can just keep going till 11. Okay, good. I will probably take that option. Okay. So, machine learning, right. So, we are not really talking about learning. I do not want to get into how humans learn and all that now, there is just too much of debate there about it, right. We will talk about what machine learning is. Machine learning is something that is well defined, right. So, in machine learning, so what you do is you are given a whole bunch of examples like this, right. So, each picture in this row is an airplane, each picture in this row is an automobile. So, I give you these kinds of directions beforehand, I am giving you this kind of instructions beforehand, right. So, if I show you this picture, you have to tell me it is a cat, right. If I show you this picture, you have to tell me it is a deer, and so on and so forth. Now, from this you learn a function, right, that given any image, I should return one of these 10 outputs. Okay. So, that is basically what what is it that we agree upon, right? Go on, I'm listening.
So there have been news stories where they had a particular image processing model, image recognition model, and they like took a picture of a dog which it recognized as a dog, and then just changed 3 pixels on the nose. After that, it stopped recognizing it as a dog and started recognizing it as something else. So like, won't these kind of errors be like prevalent in the models as we come, because we don't know how they work? So how do we know whether a small change in the image will result in a completely different answer?
I'll come to that. I have slides on that actually, believe it or not.
So, like, how do we try to remove human bias from this, like the data? Because
That is an airplane, that is a car, that's
so
a
I
bird.
don't
Yeah, there's
mean
no
like
bias
this,
here. Yeah.
Not in this case, but in normal cases, like in some cases where like data could influence.
Yep.
Yeah.
We'll come to that again. I have a whole bunch of slides on all these biases and robustness and so on and so forth. Yeah.
Sir, AI is something that we have created, right? We are the ones who are training the models,
Yep.
and we are building the technology.
Yep.
How then is it able to surpass us?
Okay. Let me ask you this. An automobile is a piece of equipment that you created. How is it able to run faster than you? Motorcycles, right? You created them. They go faster than you, right? So it doesn't mean that you create a machine, it can't do better than you. It depends on what you are building that machine for. Right? Nothing to do with kids and parents. Oh, come on, man. Next you're going to say, oh yeah, they probably fed, this was naturally fed AI and you are fed artificial chemicals, therefore AI is doing better than you. Oh man, it's not like that. No, I just don't like people attributing biological motivations to what the AI do, right? So it's not like parents and kids and anything. Right? But what I said was more of a valid argument, right? You are talking about a machine. A machine can beat you, not like a machine can't beat you. Anyway, getting back, so I thought I had some slides on how you do. Okay, so let's say this is a kind of data that has been given to you. Okay, so here I made it very simple. It's no longer images; it's simple points in a plane, right? Our images are also points in a very high dimensional space, right? So let's say that I have a 32 cross 32 image, and each pixel can take a value between 1 and 256. Right? That's a pretty large, so it's a 32 cross 32 dimensional vector where each dimension can run between 1 and 256. But I can't plot that big space here on my slides. So I picked a very simple data set where there is income and then there is age. Right? These are my two dimensions, and I want to know whether somebody will buy a computer or not buy a computer. Okay? This is also a test of your visual acuity. Can you say it? I mean, I didn't mean it to be this way. Actually, the yes color is supposed to be blue. For some reason, on this projection, it's showing up as red and salmon. I have no idea why it's showing up as salmon, but right? You can make it out. Yeah, you guys are all much younger than me. Your eyes can make it out, right? So there is that, which is yes, will buy a computer, and that is no, will not buy a computer. And I give you data like this, just like in the images with airplane and cars, right? I give you data like this. Now your goal is to, if I give you a new data point, can you answer whether it should be colored red or pink? Right? Sorry? It's right now colored gray because I don't know what's the label, right? So that's a thing that I could come up with, right? And it's actually very nice. What does it say? Hey, if your income is less than a certain level, you don't buy a computer. If income is more than a certain level, you will buy a computer. Right? So everything to this side is red, everything to this side is pink. But if you look at the data that was given to me, it's not true. Right? There are still some errors, right? There are a couple of reds here and there's a pink here and so on and so forth. And I can try to do better, right? I can go like that. Now what does it mean? What am I learning here? I'm learning a rule that says both age and income play a role, right? If you are younger, right, then your less likely to buy a computer. You need more income to buy a computer, or what is it? This is income, right? Yeah, if you are younger, you are buying a computer even if you don't have enough money. But as you get older and older, unless your income is very high, you are not going to buy a computer. So that's basically the thing that you are doing, right? So then you get there and then you fix most of your errors, but that one is still there, right? Then I can go and do something like this. Now it's becoming complicated. I can't explain it to you very easily, right? But it's become a little bit more complex. It's some kind of a quadratic, right? Is this fine? Am I doing right? I can do something like that. Just looks wrong, right? It just looks like it has suddenly sprung a big nose on its face or something, right? So, so just not right. So probably this is a better classifier, right? So basically the idea here, what have I done here is that I have taken training data, the data that has come to me with labels already known, right? And I have made some assumptions about what will be the actual decision surface look like. Will it be a quadratic? Will it be a straight line? Will it be an axis parallel line? I am making some assumptions about what kind of functions am I looking for that will map the input to the output, right? And once I have made that assumption, I am going to search through all possible lines. In this case, because it is a 2D surface, I am going to search through all possible lines, right, that satisfy that constraints that I have. So I said it has to be a quadratic, right? So I am going to look through all possible quadratics that give me the best performance with regard to the training data, right? So that's a simple way I am posing this problem. There are many ways you can optimize this, right? There are many I think I might have slide there. So basically you are given a training data, then you pass this through a training algorithm, right? So you might have things like that. So that is basically my income and my age and whether I buy a computer or not. So this is a little hard for you to define a mathematical problem on top of it. So what you do is you kind of normalize stuff, right? And then you change the labels to some -1 and +1. So -1 means doesn't buy a computer, +1 buy a computer, and so on and so forth. And then you feed it into the training algorithm. So it's going to come up with one of those lines, right? Then what you do is you actually have an independent set of entries for which you also know the answer, but you didn't use that for finding the coefficients of the line, right? You didn't use that for finding the parameters. So now you go and validate your parameters that you have found to see whether you are, otherwise what would have happened? I mean, the easiest way to solve the original problem is just to by heart it, right? Then you will be able to perform well only on those x's that I gave you to mug, right? On any other new x I won't be able to do well. My goal is to do well on an unseen x, right? So I am going to test it on this test set to make sure that I am not overfitting or I am not memorizing the original data, and try to see how will I do on this test data. And then if I do well, great, I output it. If I do not do well, I go back and make some more changes to the training algorithm and try to learn a different line, right? So there are a bunch of interesting things that are happening here. So first thing is I am treating this as an optimization problem, right? So I have a set of parameters and I have an objective function which is the number of errors that I make in the training data, right? So I have taken this as an optimization problem. I am trying to find the parameters that gives me the smallest error. So there are many techniques, and I am pretty sure you have all come across various optimization techniques already. Right? I mean, taking the derivative, equating it to 0, finding the minima or the maxima, starting from there, right? So you have found various, so you can apply any kind of, I mean, in fact, every known optimization technique has been applied to solve the reinforcement, solve the learning problem, right? And the second thing I also introduced to you is this notion of what is called as a inductive bias. Okay, this has nothing to do with the bias you were talking about, the human bias earlier. This is inductive bias, is a very specific term. So what does inductive bias mean? I have actually made an assumption about what the form of the line I am looking for, right? I said it is going to be quadratics, right? So that assumption that I made is very important, because if I do not make the assumption, if I say that line can be anything, right, what is the best solution that will minimize the error? Just to remember it, not the straight line, just to remember the solution, right? For each of these points, right? All I need to do is figure out the right answer for the training data points. I am not worried about how complicated the line becomes. I just say I'll remember each and every data point, I'll just by heart it, right. It's basically, it will be a discontinuous set of points. It will not be a line, it will not be a plane, it will not be a surface. The best solution, if I don't make any assumption, is just a discontinuous collection of points, right. Yeah. So, I don't want that. Why? Because it is not useful in terms of addressing my original problem, which is to give a classification, give a label for unseen data points. So, for me to do generalization from examples, right. So, that paradigm where I give you a lot of examples and from there I am asking you to induce a rule is called learning by induction, right. And therefore, this idea of making assumptions about what these lines are is called inductive bias, because without the bias you can't learn through induction, right. So, an inductive, the whole idea of inductive learning goes back to at least the 1700s, where there were philosophers back in the 1700s who actually said inductive learning by definition is not possible. You can't learn just by examples, because the examples will only tell you some aspect of what you are trying to learn about, right. It hides as much as it reveals to you. There are so many things that the example doesn't show that you will not be able to learn about, right. So, people, that is a whole school of philosophy going back several hundred years that say inductive learning by definition is actually impossible, right, which it is true in some sense, because I can never guarantee that I will be correct on a point that I have not seen at all before, unless I make some very strong assumption about where those points are coming from. If the points can come from anywhere, right, and my distribution can change in any way, then I really can't guarantee that I will do well, right. So, the inductive bias allows us to make assumptions about the data and actually go ahead and do inductive learning, right. So, that is basically the point, right. And yeah, so that you could make many different kinds of assumptions. I just showed you examples with just planes, right. I mean, lines in 2D are basically planes in higher dimensions. I just showed you examples with simple planes, hyperplanes. You could actually learn with much more complicated structures, much more complicated inductive bias, and that is what all these neural networks and other things